Hello, students. Section 3.5, that's what's on the table for today. 3.5, we're talking now about division. So kind of the final of the four operations: addition, subtraction, multiplication, and division. For division, we're going to use three different models. One is known as repeated subtraction, sometimes known as the measurement model. We're going to use the set partition model, and then the missing factor model. So these are just three different approaches you can have for division, ways to model it physically. Take a look at the Common Core for this one. This is grade 3. And I want you to understand when they talk about this, their terminology they're using is for teachers. You should understand these, of course, as in-depth, probably more in-depth than your students do, but they're asking you to understand and interpret whole number quotients of whole numbers. Interpret 56 divided by 8 as the number of objects in each share. So 56 divided by 8 would be the number of objects in each share. That'd be 7. So there's 7 objects in each share when you take 56 objects and you partition equally into 8 shares. Okay. So when they say share, you could even think of that as groups. Okay. So picture this. I have 56 cookies, right? And I have 8 groups or 8 plates, right? And the question is how much goes on each plate? Okay. Then in this case, 7. Or as the number of groups, they call them shares. Okay, this is the more formal language, but you can translate that for yourself. The number of groups when 56 objects are partitioned into equal shares or equal groups of 8 objects each. That's a much different question. See, in the first one, I had 8 plates set out, and I'm just going to put cookies on a plate, so I have the same number of cookies on each plate. But in the other one, instead, what I'm doing is I'm taking and I'm putting 8 cookies on a plate. And the question becomes, how many plates do I need? Okay, so very different thinking for each of these. Some students really appreciate one over the other, but the wording of a question can tell you which model to use. And this is probably the repeated subtraction, which is sometimes referred to as measurement. And you'll see why, because we're measuring something out. So I'll type that in right above it. Sometimes this is known as measurement, the model. And the second one, they call it the set model, sometimes called the partition model. Okay. All right. So repeated subtraction, you can almost see it, right? I take 7, I set them down. I take 7, I set them down. I take 7, I set them down, right? So this repeated subtraction, when you're doing it, is like saying, well, how many groups do I need? The partition model is how much is in one group. So the measurement, I want you to think of this, is how many groups is the question being asked. Well, over here, the partition is how much in one group. Always says how much is in one group. Always. All right, so let's go through this because I think this one may cause a little bit more confusion for some of you than others, just because you're maybe more used to multiplication, and even when you get to like division of fractions seems to always be a problem. Division with other numbers, decimals, can be a problem. So you might feel more comfortable with multiplication. But let's take a look. Repeated subtraction model. First off, are you going to see this in the classroom? Definitely. So, of course, they throw in a school page, and this is a school page from grade 3. And what you can see the student doing is they're taking strawberries, and they're saying each guest is going to have 2 strawberries. How many guests can she serve? So now remember, each guest is getting 2 strawberries. What am I doing? I'm repeatedly subtracting 2 strawberries at a time, right? Doop, 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 doop. And so what we're seeing is we're seeing a nice pattern here. I started with 10, I give 2 to a guest. I get 8. Now I take 2 more. I get 6. I get 4. I get 2. And finally, I have none left. You could subtract 5 times. And what we're really using is the language of multiplication here. Because if you realize that, you're saying, what I did is I subtracted 5 times. How much did I subtract 5 times? Oh, I subtracted 2 5 times. So 5 times 2 is 10, which is also the way we can think about the answer to this question, which is a division question of 10 divided by 2. We are doing what is known as the missing factor approach. Okay, that's repeated subtraction. See what I'm doing? I'm constantly removing two at a time, two at a time, two at a time. I see how many times have I done that, and I can get back to the answer. Okay. So again, I think kids do tend to like this one better than the other one, because they see there's a quicker end in sight. So if you look into some of the research, it's like I just grab things and I just start taking them away. And that is very different. It's very different than what tends to happen in the other model, which is the set model, sometimes called the partition. And in the partition model, we know how many groups there are. And so we're going to partition or break our pieces up into that number of groups. So if you have 3 friends and you have 18 cookies, typically, and just kind of showing how it tends to work, right? Someone comes up, they take a cookie and they give it to Lorenzo. Okay, there's one for Lorenzo, right? Then they take another cookie and they give it to Luis, sorry, and they give one to Lorenzo. Then they take a cookie and they give it to Caleb, right? And so there's 1, 1, 1. And then everybody gets another cookie, 2, 2, 2. And you keep doing that as long as you have enough cookies to give out. So there's a cookie here that goes to Lewis. Here's a cookie here with 4, and that one goes over here to Lorenzo. Here's one with 3 chocolate chip cookies. I give one over here to Caleb, right? And I go 3, 3, 3, 4, 4, 4. And I keep going until I'm all the way done with the cookies. So notice I'm answering a different question though. In this case, I'm answering how many did each person get? Which is basically saying how much is in one of my groups. Pick any one of them because remember, they should all get the same amount. Right? So here we go. Division definition. Oh, by the way, the missing factor model is listed here, but really, we already saw the missing factor model demonstrated in the repeated subtraction. And as we word it at the end, we're almost saying that there was a missing factor. Whew. Good times with division. Let's talk about it. Division is different. It's different than multiplication, obviously, but when I say it's different, what I mean is we have to have a term for each component in division. So when we have a dividend, that's kind of like the number you start with, the divisor, which is how much you are dividing up into, or how much per group, and then the quotient, which is the result. So I need 3 different terms here. Remember with multiplication, because multiplication was so amazing, 5 times 2 was the same as 2 times 5, I just called these things factors. I did not need a special name for each one of them. With division, right, 10 divided by 2 is not the same as 2 divided by 10. So I can't just use the same word for each one. I can't just put one word that covers both of those. Okay. All right. Oh, let's take a look at this definition here. I don't want to glaze over this. This is a this is a doozy right here. And the reason is we get a lot of our symbols here. Notice I've got an if and only if. Okay. And I've got the idea of uniqueness, and it has to exist. So there must be a solution, right? So first off, B, it says here B cannot be 0. If and only if. Yeah, you know what? I don't even like that definition. And we'll see. I think they do include this definition in a lot of textbooks. They'll say, but B cannot be 0. However, I don't think you need that. And the reason is over here, the answer must be unique. So if we take a look at the definition, 10 divided by 5 is equal to what? Your mind might even be telling you something already. So let's take a look at 4 problems here. 10 divided by 5, right? Yeah, 10 divided by 3. Okay. Let's see here. We would say 0 divided by 5 and 0 divided by 0. Okay. And you notice the reason I'm bringing this up is it says 0 divided by number is equal to a value, whatever that value is. I'm going to put the little box here just for a moment. Okay, so each one of these equals some box. If and only if that box, whatever that number is the unique whole number such that B times C equals A. So our divisor times the box gets you back to the quotient. So let's do a couple of these to see how that definition plays out. All right, here we go. So this would be if and only if 5 times that box has to be 10. Okay. So if you can find a number over here, a unique number that you put in this box, and 5 times that number gets you to 10, then that number is also the answer to the division. It is also the quotient. Okay. So I'm going to rewrite these a little bit here. Actually, I want to change my colors a little bit. I want to try to match up colors so that it makes sense. Okay, so I'm going to put the quotients in, or sorry, the divisors in red. There we go. Okay. There we go. Okay. And then the box will always remain. And that way you can kind of see which piece I'm referring to. Okay. So this is if and only if. And over here I would say 5 box times blue equals 10. Okay. Next one down, if and only if 3 times box equals 10. Okay. And then we'll say if and only if, here we go, 5 times, and here comes the box. Box has to equal 0. And lastly, if and only if 0 times whatever's in that box has to equal 0. All right. So let's see, I'll choose a different color. So I'll do black for this one. Okay, so now let's talk about it. Can you think of a number, a unique whole number that you would put into this box that would make 5 times that box equal to 10? Pause. 2. Got it. 5 times 2 equals 10. Is there any other number you could put in that box? Remember, it has to be unique. Is there any other number you could put in there to get to 10? No. So it is unique. So the answer is 2, and it is unique. So what we notice is an answer exists because we found one of them, and the answer is unique. So the top one, when something exists, we would say there is at least one answer. And the uniqueness says that there is exactly one answer. So we have to find that there is one, at least one, and then we show that there is only one. All right, let's come down to the next one. 3 times what whole number gets you to 10? Let's see here. 3 times 3, that gets you to 9. Okay. 3 times 4, that gets you to 12. We really need a number between those. There is no whole number between those. So we would say no whole number exists. Notice I'm not saying there is no number that exists. You want to be very clearly no whole number exists. Okay. So sometimes you might even be able to say, since you wanted a whole number, you might say there is no solution. Okay. And there's no solution this time because there's too few. There has to be at least one, and there's not. Okay. Let's go to the next one. If and only 5 times. Okay, 5 times what number gets me to 0? 5 times what number gets me to 0? Pause. 0. 5 times 0 gets me to 0. So you put a 0 in here. You check, is there any other number I can multiply by 0 to get to 0? You'd say no, it is unique. So an answer exists. And so I have exists and is, so 0 does exist and is unique. Okay. Now again, it has to be a whole number, and 0 is a whole number. So that works out perfect for us. Okay. Let's check the next one. 0 times what gets me to 0? So I got to think about that. I got to think about that. Michael Jordan. Let's check it. I think the answer is 23. I really do. I strongly believe the answer is 23. Now let me check it here. 0 times 23, does that get me to 0? Yes, it does. So I know some of you were thinking of something else, but it's obviously 23, right? It has to be 23. What was that? You tried a different number and it worked? Let me try it. Okay. What was your number? 12? Okay, well, let me check it here. 12. Okay, let's see here. 0 times 12. 0 times 12. Well, that, oh, shoot. I mean, that is 0. The definition said that whatever number you came up with had to be the unique value. So, I mean, definitely answers exist. We have some things that exist. We can check that. It does work. But I think we would say it's not unique. You could put any number in that you want. So this one as well, we would say no solution. And I might say no solution this time because this time there's too many. Not too few. There's too many. Okay. Now, other times in a textbook, you might say, hey, this falls outside of the definition. So the term might be undefined. Okay. But just remember, one of them is undefined because there is no solution. The other type is undefined because there's too many solutions. Okay, so 0 divided by 0 is different than 10 divided by 3, something along those lines. Okay, or even 5 divided by 0. If I said 5 divided by 0, right? Well, that's supposed to equal a box if and only if 0 times that box has to give me 5. And you'd say, there is no number. No number works. You can put anything you want in there, multiply by 0, you're never going to get 5. So again, this would be undefined, but it would once again be undefined because there are too few solutions. All right. Let's move on. Whole number division properties are listed next. And you get a nice little, so the first one we saw was the measure out. This one is the set partition model, which again is, to me, I like this one better. But some of you may prefer the other. All right. So we are going to look now at division algorithms, which is a series of steps to perform division and see if we end up with possibly a remainder. Okay, so it may not go in evenly, but we might have something left over. So we can still do the problem, we just have a little bit of a leftover. And that's the idea with this problem. If you had 32 apples and you tried to break them up evenly among 6 students, you could say, hey, everybody gets 5 apples, but I still have 2 left over. Okay, and assuming we can't split the apples up, they got to remain whole. That's as far as this goes. So a couple pieces when you do division with a remainder is with a remainder, you have to realize there has to be unique whole numbers. And the key piece here is that your remainder has to be less than the number that you're making the group size of. So for example, up here we were dividing by 6. So my remainder, I couldn't say I have a remainder of 8. Okay. But let's take a look at a smaller problem and see why that would be an issue. And I think it isn't an issue too much, but I want you to see that a student, mostly it's not an issue because you were already told as you were growing up, you can't do that. But a student won't know that. Okay, so let's take something smaller. Let's take 9. Yeah, we'll take 9. And we are going to divide it up into 4. Okay, so 9 divided by 4. We're going to see what we get. So that takes 9 objects. Let's do partition. So I'm going to make 4 parts, and we're going to see how much goes in each part. So 9, when I do this, I'll change the size. So we can say they've got 9. So there's 1 for everybody. And I count 1, 2, 3, 4, 5, 6, 7, 8. That's 8 of them. I have 1 more, but it's not enough to distribute. So I put the 1 off to the side. And I would write this down as there are 2 in each group with a remainder of 1. Okay. Now I want you to think about that though. Couldn't a student, and we can check that, right? The idea is to say, okay, well, let's check, is 9 equal to 4 times 2? That's the 4 and the 2, your divisor and your quotient, and then plus whatever your remainder is. So 4 times 2 is 8, plus 1 gives us 9. So that checks out. And a lot of times people just think as long as it checks out, we're okay. Well, let's go back and try that again. I'm going to try it again this time with, what color do I want to do this time? I'll do whole shapes this time. maybe I'll do black this time. Okay, so now picture another student comes along, right? And they're like, okay, so here's my 4 groups. And they say, okay, everybody gets 1. That's 4. And then I have 5 left over. Yeah. And they say, but don't worry, it checks out. So 9 divided by 4 is equal to 1 group with a remainder of 5. And you can check it because 9 is equal to 4 times 1 plus 5. Remember, my remainder is what I add on at the end, and I multiply these 2 numbers, the quotient and the divisor. So yeah, it does check out. That checks out. So what we do in these situations is we actually change our definition to say you need to be careful. Your remainder, if your remainder is bigger than the divisor, then you should go back and divide out again. You should give everybody a little bit more, 1, 2, 3, 4, and that's how we're going to do these problems. Okay, so your remainder is very specific. So whatever your divisor is, that becomes like the maximum. The smallest thing your remainder ever could be would be 0. So your remainder has to be between 4 at the maximum. And again, it can't equal 4 because you could make another group of 4. And the lowest would be 0. So this is what you need to do. And the remainder must be unique. That uniqueness and requiring it to be between 0 and 4 means that this student over here, even though the answer is mathematically correct, we would not call this the remainder because it would not match the definition. And in case for those of you who are the little kind of smart ass in class, yes, someone could have said, think about this as being cookies, right? And the teacher says, go ahead and distribute these evenly to everybody, and whatever's left over, you can have, right? So the student goes, okay, I'm going to give everybody 0, and I've got 9 left over. And they say, don't worry, teacher, 9 is equal to 4 times 0 plus 9. It works. But of course, that was going around what the intent of the distribution was. All right, so that's the idea. So we have divisibility. If it goes in evenly, that means the remainder is 0. We say it is divisible by, we say it is a divisor of, or we say that it divides. And when we say divides, you're going to see that coming up in chapter 4 right away. So it's going to be pretty quick. And so if it does divide, it just means the remainder is 0, and it means it is just an even multiple of another number. Okay. 123 is divided by a number. The remainder is 13. What are the possible divisors? Oh, well, the remainder is 13. So assuming the student did this problem correctly, the remainder being 13 tells you that it had to be a number where 13, my remainder, has to be less than whatever I was dividing by. Okay. And of course, it has to be greater than or equal to 0. So this part down here is good, but what I have to be able to divide this number. So let's see here. If I had 13 left over, let me get rid of the 13 and see how much would be remaining for my product. So my product would be 123 minus 13, which would be 110. So if you're multiplying and getting 110, right? You could say, well, it's 1 times 110. Okay. You can see that 110 is even, so it could be 2 times 55. Ooh, there's a multiple of 5, so I could say 5 times 22, and also 10 times 11. Now, this is where we have to use that statement. Remember, what we're putting in here is a potential quotient, right? Quotient is Q. That also means our divisor B has to be less than or equal to 13 there. Actually, the Q doesn't have to be. I wrote Q down. It should be B. The divisor has to be less than, 13 has to be less than or equal to that. So notice if I said B could be 10, 13 would fail. So 10 cannot be one of the possible divisors. I try 11, 13 is bigger than 11, so 11 is out. Also, everything less than 13 is automatically out, and it only leaves 3 components left. Those are the actual possible divisors of 123 that we would be using for this problem. Cool. Let's see here, division by 0 and 1. Let's see here. Yeah, so they're using the same definitions that I am. They're saying there is no unique number. Yeah, I also have an issue with this because if you go back to the definition, it says B cannot be 0. So by the definition, you could say it's undefined because the definition tells us so. That's why I don't like having that other piece that says B cannot be 0. So I would like you to cross that out in your books, and I will tell you to do that in class as well. I'll ask you to scribble that out because that is inappropriate. 3 divided by 0, there is no number. 0 divided by 3, there is a number. And 0 divided by 0, there is no unique number. It means there's too many. So we're kind of balancing before. It's like the Goldilocks principle, right? Too small, too many, just right. The only problem that was just right would be 0 divided by 3. Okay, so in general, division by 0 is undefined. That's a general thing that you can take with you. Yes, it is undefined. However, the reasoning behind it is not the same. Sometimes dividing by 0 is too few answers exist, and sometimes it's too many answers exist. So there's a nice little grid here that relates the operations. Again, it relates them through the models. If you're going on in mathematics, this is not the way that you necessarily want to think about it, but for what you're doing in these grade levels, it's a good introduction to see how to kind of view things. Right, let's see here. It does talk to you a little bit about closure under division. I'm going to leave that one to you at this point because I want you to think about how division would potentially work with closure. All right, exponential property using the definition of division. This is fantastic, right? This is actually pretty nice. So if you had to divide and you had exponents, some of you might prefer to write it instead of horizontally, you might prefer to write it this way. And I'm showing you that because if you write it with division with the horizontal bar, sometimes it might kind of make you think. I don't know why I almost wrote 2 times 6. 2 times 2 times 2 times 2 times 2 times 2. So kind of take the 6 and remember to write it out because it's multiplication. 2 squared, though, would be 2 times 2. And then this is where you get to use your algebra skills, right? 2 divided by 2 is the number 1. 2 divided by 2 is the number 1. So really, these become really fancy looking number 1s. So 1 times 1 doesn't give you anything. And the end result is 2 times 2 times 2 times 2, which is 2 to the 4th. So a really cool piece of exponents is when we're multiplying with the same base, we add the exponents. When we're dividing with the same base, and this is a big piece, it has to have the same base, you just subtract the exponents. Yeah. Okay. And it says M and N are natural numbers, I guess. So that does exclude, when it says natural numbers, it would exclude the fact that N could equal 0. If N equals 0, then really you would have a number to the 0 power. And we've already talked about how a number to the 0 power is 1, as long as a does not equal 0. So now if a is a natural number, it does not equal 0. But I want you to know n could be 0. N could be 0. Yes. Okay. So there we go. They have a quick little proof in here. I'll let you take a look at it. They're showing you why it always works. By the definition of division, the division works if and only if the multiplication works. And the multiplication works, you would add the exponents together. And now since you have the same base, the exponents must be the same. So x plus n has to equal m. You subtract on the other side. So your x, which is your exponent, must be m minus n. And that's exactly what we see in the formula. All right, now here they're going to use base 10 blocks to develop the standard division algorithm. The standard algorithm is the idea of moving from left to right. Some of you think of this as long division. Hopefully we'll have time to show you what short division looks like, which is pretty awesome. Okay, so we're going to do this with partial quotients. This is oftentimes the way you would want to start this, partial quotient wise. So what we're going to do is we're going to do 6 goes into 726, which would be 726 divided by 6. Okay, so what do? Lay out your base 10 blocks. Then make as many groups of 6 with the highest place value possible. Okay. So 6, there is one group of 6 that I can make here. So I put a 1 in the hundreds place because it's one group of 6 pieces. Each piece is 100 units. Okay. Now take a look at what you have left over. I cannot make any more groups of 6 out of these. So take your group of 10, which is your 10 block, and break it up into 10 longs. Do I now have enough to make some groups of 6? Yes, I can make 2 groups of 6 out of the 10s. So I put the 2 in the 10s place value to make sure everyone knows I made 2 groups of 10. Okay. Next, and it is equivalent to 20, right? 2 groups of 10 is the same as 20. One group of 100 is the same as 100. And then you say what's left over at the end. I have 6 individual ones, which would be one additional group of 6 in the ones place value. And I have a 0 because there is nothing remaining. Okay. There it is. This is the standard / traditional algorithm. Okay, you line things up, you subtract. We'll teach the division shear in class, which I think is fantastic, but that's the idea. Now, personally, if you reason that one carton holds 32 popcorn bags and 10 cartons hold 320, so this is a different problem. This is 4,224 divided into groups of 32. Now notice that a carton holds 32 popcorn bags. So we want to figure out how many cartons can we make. So take a look. This is the idea of partial quotients. You say, wait a minute, 10 of them would be 320, so 100 of them would be 3,200. I can definitely make 3,200 because I have more than that. So take 100 of those groups and subtract them. Now you only have 1,024 remaining. You just made 100 cartons. Okay. Now you have 1,024. You say, well, wait a minute. I could definitely make 10. So you could take away 320, and you could actually take away another 320 and another 320 until you get down to below 320, because you know every group of 10 cartons would be 320. Now that leaves you 64, and some of you could see 64 goes in there twice, but if not, just take away some additional groups of 32. The last step for this algorithm is to simply count up how many groups of 32 did you make. You had one group of 100, so 100, 10, 20, 30, that's 130, and the last piece would be 2, so 132. Now you can shorten this algorithm down. So if you take a look, what do I mean by shorten it down? I guess what I'm saying is maybe you would see that you could do 3 of these chunks at once. And so you could just do 30 groups of 32 in the middle. And maybe you can see that I could do these 2 at the end, so I could just do 2 of them. Both of these work. No way is necessarily better or worse than the other. And for a student struggling with division, if they can't see how many times it goes in, instead of sitting there kind of just getting frustrated, you could say, hey, why don't just say, do you know it goes in 10? I know it goes in 10. Okay, let's do that and see what remains. Now at least the number's smaller. Now the student is making progress towards the end result. So they're feeling much better about kind of where they're headed. All right, partial quotients algorithm, there we go. If you were to do this vertically, which would be a little bit more of the traditional, instead of writing it on the side, the traditional tends to write things above. We tend to write this way, which will be known as scaffolding, which is just building up. So instead of putting just the number 1 in this place value, we would tend to write 100 to remind everybody that it really is 100 groups of 32. The traditional one that you might have grown up with, your teacher would say, how many times does 32 go into 42? And you would say 1 time. But the issue with that is it's not 42. The number 42 is nowhere in this problem because the place value shows you that this really would be 4,200 is what we're thinking about. How many times does 32 go into 4,200? And that's why you would say 100 times. That's why we write the 1 in the hundreds place, is because really 100 times 32 gets me 3,200 as we go through. Okay. Then you can continue on and you say, well, how many? And again, if you're off, you just write another group of 100 in the hundreds place. So scaffolding is like you build up to your answer. Okay. So think of it like the Price is Right. You got to get under it. If you go over, you're done. But if you stay under it, you're okay. So that's the idea behind scaffolding. All right. Let's see here. What else? Here's the partial quotients problem. All right. That's another school book problem. Here's this division problem. So it looks like somebody has done this division problem. Explain what was done in each step. This might be something I put on a test. I'm not sure if I would put something like this exactly on a test. I think for something like this, I might give you kind of a typical student issue or error that they tend to make, so you can kind of determine what happened here. And then you have division in other bases. So we'll be doing this part in class. We will not be doing it with the base blocks. We'll be doing it with poker chips because we'll be in Fivania at that point in time. Okay. Yeah, I think that'll be helpful. So here's a couple with different number bases. And then mental computation and estimation. So mental computation is to get the exact answer. Okay, so the exact answer sometimes is you break up the dividend, you split it into pieces that work. I do this frequently, but I probably do it on problems. This one is pretty obvious because 7 goes into 42 and 7 goes into 56. Let me see here. What would be another problem that it would be a little bit more challenging to tell whether 7 goes into it? Let's see here. What if it was 4326? Okay, so does 7 divide this number? And again, if I was looking at this problem, I might struggle just a little bit with it. So what I would try to do is break this up into some chunk that I know. 7 goes into 42. That's a really close number. And it leaves me 126. And 126, it's bigger than 70. Maybe it's bigger than a lot of these pieces. I'm just going to take 70. I can take 70 off of this. And so what I'm doing is I'm breaking up the dividend. And so I could say, does 7 go into 4,200? Yes. Does 7 go into 70? Yes. Does 7 go into 56? Yes. And then I can just write down how many times. 7 goes into 42 6 times with 2 zeros. That's 600. 7 goes into 70 10 times, and 7 goes into 56 8 times. So I'm able to get that solution pretty quickly. Okay. So again, those are what sometimes they refer to as compatible numbers, but either way, sometimes you have to combine these techniques, breaking up the dividend and using compatible numbers. I think is a really nice way to do division, a seriously nice way to do it, especially if you're doing it in another number base. Find something you do know and then use it. Estimation, find compatible numbers. That's really the biggest way you're going to do estimating with division. There's just not another better way to do it. Okay. All right, last piece here. We've gotten through addition, subtraction, multiplication, and division. And what we do is multiplication and divisions are performed before additions and subtraction. And you might want to highlight this. They are performed in the order they occur from left to right. This may or may not be what your teacher told you at a previous course. I don't know. Occasionally, people do refer to PEMDAS, and they say this is the order of operation, which does make it seem that multiplication comes before division. That is not the case. So multiplication and division are a very special group. They are very friendly, if you want to think of it that way. Either one goes first, and this is from left to right. And likewise, your addition and subtraction are extremely friendly as well. And so they go from left to right. Okay, so if there is no parentheses written, at all, you look through and you look for multiplication and division, and you do those in order from left to right. Okay. Then once you get done doing that, then you go back through it again. So this is kind of a tedious process. It actually makes it seem like, hey, could you just put the parentheses down? It'd be like super helpful. And it probably would be super helpful. But if there are no parentheses down, you have to be able to do these types of problems. So here, 8 minus 9 divided by 3 times 2. And they like to do the dot. I guess I should use the dot as well. Plus 3. If you were just reading this, parentheses, none, exponents, none. If you just read it from left to right, you really might think multiplication comes first. And so you would do 3 times 2 to get 6. And that is not the proper way. So the first thing I would do is I'd go through and I'd say multiplication and division. I do have some of those. I'd flag those down. There's multiplication and division. I do them in order from left to right. So 9 divided by 3 would come first. And personally, I would rewrite the question. And then I have only one of the multiplication and division, which becomes this. Lastly, I have addition and subtraction. Once again, if I just read from left to right, I would do the addition first and then the subtraction. That is not the order of operations. And we'll see shortly. Honestly, we need to get to integers first, but what I want you to see is that really subtraction doesn't exist. And so that's why doing subtraction first, going from left to right, is the proper way to do it. Because, and we'll see this later, 8 minus 6 is actually defined as 8 plus the opposite of 6. This is the actual definition of subtraction, is to rewrite in terms of addition. So really, you'd only have addition. And the same is true with multiplication. Okay, so if you had division, 8 divided by 4, we could rewrite this as 8 times the reciprocal of 4. Okay, once we get to fractions. So really, division is like a placeholder that we use temporarily. Honestly, it's probably better if we didn't use it at all, but it also means we'd have to be dealing with some complicated pieces. So we tend to use it for the time being, and then we try to move past it. So truly, when you get to higher level math, you really think about this as parentheses, exponents, all multiplications, and then all additions. And then we don't have to have the same issues that you might have had growing up as to which one do I do first. Pretty cool stuff, at least in my mind. Let's see here. And then we're into the assessment. So that wraps it up for me. All right, there you go. We're wrapping up chapter 3. Take care. Off you go.